see how much the accuracy is changing when we use undersampling method, and then we can draw some conclusions on that. So the first undersampling method what we have discussed, that was the random undersampling method. So this is the whole code. So going now. Already we have discussed the whole part here, just to make you refresh, just telling once again here those things. So we have to import here pandas as PD. By PD we are invoking the file here, the data frame, and it is stored in a variable that is F1. And now from F1 we have a class here, class, it is written as class, and we have a different kind of classes here. And how many classes of 0th and how many classes 1 means different classes. It would be counted by this function, and this function is available in the panda. This is the function. So by this one we can count how many of which class are available. Generally using this function we can find how many times the different number of attributes are available in a particular, say, data frame. So here we have taken the data frame that is F1 class, and here we have this function. And after that, what we have done, after that we have called here the random undersampling. And for the random undersampling, again we have to call one package, that is this here. So the package for that one is called imlearn.undersampling. And under that we have here a submodule that is called undersampling here. And the undersampling function is called here. Generally, if we don't assign anything here as an argument of the function takes 1:1, means the ratio is 1 here. And then we have, say, split the F1 as a X and Y. Already this part is discussed because F1 contains, say, data set that is a thyroid data set, and this is the split. And then we resample using which one? RAS. This RAS is given here. This RAS is called in random undersampling is called in RAS, and this now the model is fit with this RAS. A resample X comma Y. Resampling is done actually fit resample X comma Y. We have to give the input and the output. Here input is X, and we're having 4 input 0, 1, 2, 3, 4, 5. So here try to understand, here we have taken the inputs. So the first column, second column, third column, fourth column, these are the inputs, and inputs are stored in X. And here we have written input comma output, and then resampling is done. And finally here we have a printed out here, means we are going to print out the resample size of the database. And here we have written print counter. See here, counter Y, this ROS. This ROS is for which one? For Y. And now this counter is used to count how many discrete values are there. The same task can be done using value counts. The same task can be done using value tasks. Try to understand. But here we have used a different function, and this function is available here. So that's why this function is imported. This submodule is imported here. You see here the from collection import counter. So it's a submodule. In this submodule we are having this function, and whenever we're passing an argument here, then automatically it finds how many discrete values, how many times are there, it would be printed out. So the task of this function and the task of this function both are same. Yeah, just here we have shown you two different kind of functions, and after that we are doing, we are concatenating X and Y together, and column wise, that's why X is equals to 1. Then we are printing out here. So finally you can see once, then we'll discard one by one, then you can see here that's the output. Hey, here is the output. You see here, using this function, you try to understand, this is the whole output. So we are, yes, I'm going to show you one by one. Already we talked about here. After here, we are going to find how many classes are there. So cutting this one and printing out only. So using this one, we can find out how many items are there for 0 class and 1 class. Using this, hello.
Have you seen?
So here, see here, using this function, we can find out how many different classes are here, right? So if we add this one, expanding one by one, so expanding here, this is called now, and now it is resampled here. And after resampling, we're trying to find out here how many resampling, how many patterns are here, how many samples are here. So right now, simply see here. After resampling, because already I told you, if you don't have anything, it means what? The ratio is 1. It's now we undersample the data. So initially you see here, the 0 type is having 359 times, and one class is having 69 times. So as we're doing undersampling, that's why the majority instances would be deleted from here. And as no ratio is mentioned, that's why there is 1:1. So one class is how many minority? 69. That's why now the majority becomes 69. So this is the output. Now to run it, because again you have to see the output. If we make this one, so we made that a data frame, a whole data is stored in a variable that is f2 here, right? So we just already I talked this one, right? This x and this y, they are concatenated. This one, this and this. So if we concatenate those things together, then this is the total file. So here we have f2. F2 is the total file here. This is f2. This is f2. You try to understand. This is f2 because this thing is done for which one? For training. We split this one as x comma y. Training is done, and we have created number of samples. We have created undersampling. We have done undersampling. After that, now after doing the undersampling, the outputs are stored in X rows and here Y rows. Now X rows and Y rows, they are the different. They are the different. If you want to see here, that we can see here, they are different actually cutting here. So now we can find, you can print here, very easily print this one, rows, X rows. So now printing out this one, then we can find the value of the X rows only here, right? So X rows is here. 1, 0, 1, 2, 3, 4. And Y is totally different. So we can keep here Y also. We can see the output Y here also. So Y is given here. So by finding the output at a time, you can get only one output. If you want to see both together, then we have to write here print. Within print, we have to be this one. And then again here, this is a print. So now we can see both together. They are different actually. See here, they are different. So here we have a X rows, means the inputs 1, 2, 0, 1, 2, 3, and 4. And here we have the output. See, then here we have the output 0, 0, 1, 1 kind of thing. So now we have a 2 data frame now. Somehow we have to merge it. And for that one, we have the code this one. By this one, we merge. No, this one is not. So taking from here. So taking from here now the resampled. It is done here. So finally now we have F2. So size of F2 is this one, 138 rows are there. Means 138 observations are there in the undersampled database right now. So now already we know the accuracy of the thyroid, this is around 97%. So now if you do the undersampling, so in decision tree, what would be the accuracy? We're going to check now. With the GT, we're going to find now the accuracy with GT here. So here simply we have the code of the GT with the same setup, experimental setup. We didn't change anything here. Just F2 is taken because now F2 is the refined database. F2 is the refined database. See here, F2 is the refined database. So this F2 is the refined dataset now. So this refined dataset is used here in the GT, and we are trying to find out the accuracy, how much it is. So it is 100%. It gives 100% accuracy here. If you undersample with 100%, then the accuracy is how much? The 100% accuracy it gives. Because it depends. It doesn't guarantee you. Try to understand. If you feel that if we do the undersampling in each and every cases and if we will get 100% accuracy, that is not true. This is only because of the behavior of the database. The behavior of the database is like that. That's why the accuracy is 100% here. But especially, I'm telling you, on an average, the explanation says that if the database is small and if we do the undersampling kind of thing there, generally on an average, the accuracy drops. But in this case, as the characteristic of the data set is a bit different, that's why now we got here 100% accuracy. Now we're changing here. Okay, fine, we're changing to how much? We're changing to, this is undersampling 1:1, we're getting 100%. Now, if you get the same, if we do the same undersampling, and if we change it to the ratio that is 0.5%, then what happens? We're looking on that. See, so now we are doing the same thing. I'm not going to explain right now here the undersampling. We're doing the same undersampling, random undersampling, but if you try to understand now, the ratio is 0.5. Now we are not doing 100, means 1:1. That is 1:0.5. Already you know this term very well. So now the ratio is 0.5. If you do like that, then what is the accuracy trying to see now? So now this is now F2. We have this one. Just we need to run the same code here because in the decision tree we have it in all those things, and the file is stored as F2. And F2 is used in the decision tree, so there is no change. You try to understand, just here we have changed only this parameter. Now it is 0.5. Now it is 0.5, and finally the data set is stored in F2. And during training of this random forest, we have used F2 here. So looking now, how much is the accuracy? Here, sorry, this one. Looking how much is the accuracy now? Yeah, now if we use 0.5%, then the accuracy becomes 0.97. So in this case, there is no improvement. Rather, the accuracy drops because earlier we had a 100% accuracy. Now the accuracy is 0.97. This is for undersampling, try to random undersampling. Apart from random undersampling, we have studied which one? We have studied near miss. So now we're going to see the near miss. If we apply the near miss, then where is the outcome? See here, so we have a near miss, and initially we have taken 1:1. Means the ratio would be 1 here initially. See here. See here, the same thing, there is no change. Just here, try to understand. We are going to use now near miss. This near miss is a submodule of the package, this one, imlearn.undersampling. That's why we call this now submodule under this package. Now this near miss, we have a function as near miss, and within the function we are passing two parameters here. The first one is the version, that is version 1, because in near miss, if you can recall that we have a 3 versions. See here we have a near miss 1. So if we want to use the near miss 1, then that is called version number 1. And if you can recall, in case of near miss 1, one of the tunable parameter, that was the value of k, how many nearest neighbor we are going to consider for that. So in this experimentation, we have taken the number of nearest neighbor, that is 3, and near miss, and it is stored where? As undersample. Undersample is a variable. The whole function is invoked and it is stored in undersample. Now this undersample is used here. This see here, undersample.fitResample x, y. Already we have talked about in case of random undersampling. Same thing, just the variable name is changed because now this function is calling this variable. We have changed here only. All the things remain same. There is no change. Now we are running here. So running here. So 1:1 now. Try to understand. So we have minority instance. How many? 69. That's why this majority class 0 now becomes 69. So 169. This is a minority pattern or minority observations, because the class 1 and class 0 is majority. And see here, after doing the resampling, the number of majority instances becomes 69. So equal number of majority and equal number of minority now we have in the database. And the name of the database is what? That is F2. So now we use the same function, same decision tree. There is no change. So this is the decision tree. You try to understand whenever we are doing the program here, the value of f2 is changing because you're having basic idea of basic Python, and also you're having basic idea of C programming. So whenever we are changing the values, the current value will be stored to a variable, that is here f2. So now we are running here the decision tree with same setup and looking how much is the accuracy. Here, if we use the near miss and if the ratio is 1, then the accuracy drops. Now the accuracy becomes 0.85. So now we're going to use the near miss 2, and now we're not going to use a separate ratio, because again you try to understand here the ratio can be used. Try to understand here. I'm showing you if you want to use a ratio kind of thing. We didn't mention here the ratio. It means 1. It checks ratio 1. Means equal number of minority and equal number of majority. See here the version 1 and nearest neighbor 3. And we did not mention here the ratio. If you want to mention the ratio, then we need to mention the ratio by comma here. So we are looking with some other example, that is near miss 2. Now we're going for the one tunable parameter is there. Try to understand which one is the tunable parameter in near miss 1. The tunable parameter is this one, the nearest neighbor. So in this example, we have taken the nearest neighbor, that is 3. So now we can change it. So now we're changing it to 5, looking how much accuracy is changing. So we have made it 5 now, and running here. Okay. So now we are doing the experimentation where the k nearest neighbor, the value of k is 5, and already this part is over, and the resample database is stored in F2 now. And looking here, how much is the accuracy? So see here the accuracy increases, and now it becomes 0.96. Earlier we had 0.86 or 85 kind of thing, but now it is increased to 96%. So you try to understand in case of near miss, the tunable parameter is the values of k. So whenever you are going to use k near miss 1, then you have to tune, means you have to change the values of k. And finally, based on certain train, you can say the value of k is exact for this experimentation. So it's a try to understand, it's a tunable parameter. So I'm telling one thing, whenever we have a tunable parameter in any experimentation, then we have to tune it, means we have to change the values in say different ranges, and finally we have to conclude based on the result which range is good for that. So that part is over now. We're coming now near miss 2. In near miss 2, just we are not using 1:1, we are using 0.5% ratio. Ratio is 0.5, so that you can understand how to write if you want to change the ratio. So simply here, now our objective is which one? Our objective is to run near miss 2. Again, you try to understand near miss 1, near miss 2, all are the function of this sub module, and that is near miss only. That's why we are calling only the near miss, only near miss. So this one is redundant here, we can omit, there is no problem. Fine. So we have a near miss, and now we have used here near miss, and the version is now 2. So means we are going to use now near miss 2. And the number of nearest neighbor, the value of k is how much? And here it is 5. And sampling strategy means the sampling rate. So how much say we want to use here? 0.5%. So 50%, that is 0.5. So we have used here 0.5. This is the ratio. You can recall, I think the ratio already we talked about earlier, right? So now all the things are the same. Resampling is done here, and the resample database is finally stored to a variable that is f2, same variable. So we're running here. That is done now. The answer ratio is how much? 0.5. That's why the minority class instances, number of minority class instances is 69, and number of majority class instances is here 138. See here. This is after sampling. Resample database shape or data set shape here. We have done this part using this function. And we added all those things here. Now the total number of samples becomes how many? 207. Now we are using the decision tree with the same setup and looking how much is the accuracy. So here, running this one, and the accuracy is 100% here. Here the accuracy is 100%. So again, you try to understand, if you want to use say near miss 2, and if you want to make the ratio 1, then we need to cut this one simply, right? We need to cut. If you cut this one, then it becomes 1:1, means equal number of minorities and majorities. And we're doing that one here. So running exactly here, see here, the resample database is stored in F2, and how many resample data are there, you can see here. This is the output. So class 1, total number of minority instances is 69, and total number of majority instances again here 69. Because here we had a ratio that is 0.5, we have omitted that one from here. So by default it takes ratio 1. So now the resample database is stored in F2. Looking, if it is ratio 1, then how much is the accuracy if we use near miss 2? And looking here, so the accuracy drops, and that becomes 0.85. Now finally we have a here that is near miss 3. So now going to use the near miss 3. This is near miss 3. And here same thing, all the things are same within the same submodule. Near miss version 3 is available, just we need to change here the version. We have written here near miss and the version equals to 3. Means we are talking about near miss 3 now. And here we have given the nearest neighbor how many? This is 5. And if you can recall properly, see here, in case of near miss 3, we did not have the ratio, because the whole ratio is controlled by k, where k is a tunable parameter. In this case, k is only the tunable parameter. We cannot use the ratio here because the value of k maintains the ratio. When you discuss k miss 3 and near miss 3, already we discussed this part. So here we are having only one tunable parameter, and that is k. So you can see here in the code we have written, and that tunable parameter we have chosen here, the value is 5. The value of k is 5. So now looking, if the value is 5, then how many patterns will come in the majority instances? Looking here, if the value of k equals to 5, the number of majority instances become 41. Already during the discussion we talked about the number of majority instances which will be in the refined database totally depends on the value of k. Generally, if the value of k is higher, then the number of majority instances can be higher. If it is lower, the number of majority instances would be lower according to the working principle, because we have discussed that one, right? So here now, if we make it, it's 5, then total number of majority instances become 41, and the minority instances is 69 here. And now the refined database is stored in F2. Now the same decision tree, now we can use something is that the number of samples to be selected is larger somewhere. I think something happened. The number of samples. But still we can do, there is no problem here. 110, so we can run now the decision tree. Where is the decision tree? Here is the decision tree. So here is the decision tree. So now we can do here simply, right? We can run it and then we can see. So how much is the accuracy? The accuracy, see here, if you use the value of 5, and that is a 5 here in near miss 3, then we are getting the accuracy that is 95%, right? So already talked about which one is the tunable parameter. This is the tunable parameter, right? The number of nearest neighbor. So now we're changing that one. So we are making this one as 3. Looking, so if it is 3, it is believed that the number of instances will be lower. Yeah, it is lower now. The number of majority instances now becomes 28 only. And the minority instances, there is no change because we are doing now undersampling. So total number of instances now, how many? Only 97. So if we use 97, this refined data set to the decision tree, then why is the accuracy looking? Yeah, accuracy is 95%. Now we're changing to 1, looking how many. It becomes very less, I think. When it becomes 1, looking how many patterns comes under 10 pattern only. See, when the value of nearest neighbor is 1, then we're getting only how many? We're getting only 10 majority instances, and then the total number of instances in the database becomes 79. With the same setup, we are running now the decision tree, looking the accuracy is 87%. So we are changing it to 10. To make it 10, possibly the number of instances will be higher. Here, that is, we have made it 10, and now the number of majority instances in the refined database, that is 64. So looking, making it say 20, and looking how much it changes here. So if it is 20, yeah, if it is 20, then it's 69, and this is 69. So looking and running, again, when it's running that decision tree and looking how much is the accuracy, and the accuracy is 89%. So you try to understand in case of my endeavor is here to show you that in case of near mystery, the tunable parameter is k. So you have to change the k and you have to find a trend, and then you have to conclude something if you want to use that this one or this algorithm to a particular application. So whenever you want to use this in a particular application, then you have to vary the number of k's and you have to conclude something so that a rigid kind of conclusions can be made. Then it will be a kind of analysis that can be a good work. So already talked about which one? We talked about all the undersampling methods. So whichever we have discussed about. Here I have more, but I'm not going to discuss all those things here. We have a condensed nearest neighbor, not going to discuss. Now, one concept we have discussed here, if you can recall properly, see here, one concept is there more, and that is we can combine the undersampling and oversampling together. Then finally we can find out the accuracy of the classifier. So now we're going to do one of the experimentation with the combinations. Here we are combining the random undersampling and oversampling. I'm going to see how the accuracy improves here, looking on that. And you try to understand the whole code here, just not only the code I'm running and you will run only. You have to understand here. See here we have F1. In F1 we have invoked or imported the actual database, that is a thyroid 1. It is now available in F1. Now we can count the number of classes. Here it will be class, otherwise you will not get. Fine. And here it is broken down into training. It is broken down into input and output. In input we are having the attributes, and output we are having the class levels. And here we have done, which one? We have done the oversampling, and the oversampling rate is 0.5 here. So initially we have done random oversampling on the data set, and we made it 0.5. So somehow what we have done here, we oversample the data. Means the minority class instances are increased here. Fine. And then which one? Then we say resample. We then train it here, resample the database. Here resampling is done. And then this is the number of resampling database, right? This is the number of resampling database after the random oversampling. So whenever we do the random oversampling, it means what? The minority instances should be higher. So you can see here. So minority instances, how many here? 69 generally in the actual database. So oversampling is done and it is expected, and the ratio is how much? 0.5, and it is expected that these minority instances will be increased. So here, see here, the one class is increased, and that is 179. We have done only here the oversampling. That's why majority instances, there is no change in the majority instances. In the majority instances, we're having 359. So still we're having 359. Just we have oversampled. And here the count is shown by this word counter y, because in y we're having the output now. There are changed the name now here, right? You can change the variables. So we have seen that the number of minority instances is increased, and that becomes now 179 now here. So in the same, in the refined database, what we're going to do now, we're going to do some undersampling, right? So here just I have executed random undersampling. You can see that here we have a random undersampling. Fine. In random undersampling, we have a sampling strategy, that is we have chosen here, that is 0.9. So that we don't need to, we are not going to undersample the whole database. We want to keep some of the instances available in the database so that the number of total observations in the database will be significant. That's why I have given you 0.9. So you can make it anything. This is only the experimental purpose. So here in the undersample, this is invoked, the function is invoked with this ratio, and now that is available in under. Now this undersampling is done here. This undersampling is done on this resampled data set. Now it is resampled. You try to understand here we have the resampled one. Then now this undersampling is done in this resampled data, and again we are making the resampling here. Because here in this case we are doing which one? We are doing undersampling. That is random undersampling. So after random undersampling, this is the number of instances which is available here, the counter y rows, because here now I just kept the values of all the outputs in y rows, and the inputs I kept in x I rows. So after random undersampling, now we can see the codes here. So after random undersampling, now it becomes this one, because here during the undersampling, the minority instances will not be changed now, the majority instances will be changed now. So already after doing the oversampling, we have 179 undersampled database, say minority instances. So these minority instances are intact, there is no change. The changes occur only here in the oversampling part, this majority instances. In the majority instances, we had how many? 359. But after doing the random undersampling, now the total number of oversampled data, so majority instances is 198. So this is the ratio of minority instances and majority instances in the final database after doing random undersampling and random oversampling together. And finally,
Unmute yourself, sir.
so now here we have, we just concatenate both this and this together, and it's stored in F2. Already we have discussed F2 here we have. Now the whole database is stored in F2. And the size of the database we can see here, that is 377. Now we can use the decision tree here, then we can see how much is the accuracy. So decision tree is already available here. So we can take one of them here, that we have the decision tree. Yeah, this is the decision tree that we have taken. And from here, fine, we're going to see how much is the accuracy. Now looking, yeah, now the accuracy becomes 98%, right? So after doing the combination of undersampling and oversampling, we are looking at the accuracy becomes 98%. So again, you try to understand here we have given the ratio that the one ratio is 0.5 and 0.9. Now we can change the ratio, you can shuffle it to optimize, because these are the tunable parameters. So you can tune those things, you can change the different combinations and different ratios, and finally you can tune the output here. Fine. So we have seen here, if you combine the majority and minority, so oversampling and undersampling together, then there is a hope that the accuracy of the classifier can be improved if the database is imbalanced. You try to understand this kind of treatment is given only if the database is imbalanced in nature. If the database is not imbalanced in nature, then there is no need to do those kind of things. Now you have a question, sir, how we can understand that whether this is imbalanced or not? By the counting, you can see that how many majority instances, how many minority instances, or you can use say histogram, by that you can understand, right? So after that, this undersampling and oversampling, we have a topic, and that is what? That is feature analysis. In feature analysis, we have seen number of things here. In a feature construction, if I have two features, then we can create one more feature here, right? We have seen. Now, if you want to do the same thing in say Python, then how we can do? So looking on that now one by one, and you try to understand the code, right? So here we have the code. Here we have the code. So going to do that one. So now this one we have, right? So imported the pandas. Pandas is already available. Just I have written here imported. It is available already. And we made two lists here. It's a list, room length, and this is another list. And already I told you, if you want to use in pandas, then this list has to be converted into data frame. and the list can be converted into data frame. How? In that way, right? In that way, because it's also a list. So we have a 3 list here. This is the first list, second list, and this is the third list. So now using this function and in this way, in this syntax, actually we can convert it into data frame. So it is written as pd.dataFrame. Now we have given the name of this one, length room. The title of the name means room length. In the data frame will be length. So that this is the title in the data frame. Try to understand. For whom? For room length. So room length is given here, right? So that's why the title which is to be given in the data frame, that one has to be written with a single colon, single quotation. Then we have a colon here. Then the list what we want to assign to this data frame. So this is room length. So room length will be assigned now to length. Similarly, here we have a breadth. So breadth would be written within single quotation, and then which one colon. Then again we have here which one, room breadth. So room breadth will be given to this one, to this column of the data frame. So name of the column in the data frame would be breadth here. Try to understand. Similarly, here we have a type. So room type, the values of the room type would be assigned to type, and type would be the title of the column. Fine. So if you want to see that one, just we are discarding all those things from here. Discard. Just we have created the data frame, and now this data frame is available in.
Participants, please.
Done. So now this data frame is stored in data. This is the data. The data frame is stored in data now. So now we're going to see the data. See here, the data frame is created now. So we have a length here. Length is the title of the data frame, and this breadth is the title of the data frame. Type is the title of the data frame. Now we have. Fine. So now what we want to do? We want to create one more column here. So for that one, see here, simply here, what we have done, we have inserted one more column, and the name of the column is area here. So we can define like that. If we want to include one more column in a database or data set, which is in the form of, say, a data frame, then that one can be included like that. See, okay. So this is data, then area. Data is what? This is the name of the file. And here, whichever column we want to give, then we have to write the name of the column within single quotation and then third bracket. And now the content is given on the right hand side. In the content, what do we have? The content, what do we have? This is data length. This data length is this one into data breadth. So if you write like that, then its corresponding values will be multiplied. That's the meaning actually, right? So in that way, actually, a new column would be created in the data frame, and that is area here. And that value is now available in data. We didn't change the name of the database. So that's why if we discard this one, and if you see the value of the data only, so see, you can see one more column here. See here, and more column here, right? We have more column. Here, how many? We have 1, 2, 3. Here, how many? 1, 2, 3. So if we want to make one, say, gap between that, then how we can make gap? Simply, if you write in Python print, then automatically it print this one, then automatically goes to the next line actually, right? So now if we execute this one, then automatically this comes to the next line here, next line here. So just here we have included one more column, and the name of the column is area. And what is the content? The content is the multiplication of this and this. This is the column, right? But if you try to understand here, what we have, so here the area is inserted here, and finally the price is here, or whichever thing is there. Here we have, say, type, big, normal, whichever kind of thing. This is a classification, and these are the inputs. So classification can be here. So this arrangement can be done simply in Python. Simply, just you need to change the sequence of the columns in the data frame. So it is stored in the data one. So name of the database is data. Now we are writing the column name. You try to understand this is the sequence, and this sequence matters. the sequence in which you have written this line, in that sequence actually the data will be stored in the database, and finally it is stored in data 1. Okay, so now, so how we have stored those things? Already we know if we want to assign and a multi-dimensional data in the data frame, how to do? We have to take the double third bracket. So we have taken double third bracket here. So we have a data, an initial first one we want to take, that is length. Second one we want to take, that is breadth. Third one we want to take, that is the area. And this is the fourth one. And again, I'm telling one thing, if you want to remove some of the column directly from here, so if you omit some of them from here, then automatically it will be omitted from here. So I'm showing you, right? This whole part is stored now where the whole part is stored in, say, data 1, and data 1 is printed out here. Looking this one, running this one, we are fine. Simply now we can see. Now this is the data frame here we have, right? So length, breadth, area, and here we have a type. So if we want to omit one of them simply, so we don't want to. Say for an example, say corrupted data removal. And now say breadth is having some corrupted data. You want to delete that one. Well, fine, delete it, no problem. So deleting this one, deleting this one. We have deleted and we kept only 2. So now looking whether working or not. Yes, working. So we have only 2, length and area and time length. In that way, you can add, you can say delete very easily the columns. So we have seen here that how if you want to construct the data, then how we can construct. Just you need to write the formula here, right? You need to write the formula. Then automatically the column would be created in the database. So in this case, our objective, our NDB was to make the multiplication of length and breadth. So we have done simply that one here by this one. Okay. So now after that we have another one, and we had which one? Now we had coming. So here. So we had some values. Looking. Yeah, this is now dummy variable. See here that in the presentation, what we have a such, if we have such kind of things, and if you want to convert into say numerical discrete variables, then somehow this kind of column have to be created. Now how we can create? Simply we can create by dummies, get dummies. There is a function available. If you write the function get dummies, then automatically it does. So see the whole code here. So now we have this one. Simply again, we are creating the data frame. Simply we are creating the data frame. Not explaining too much. This is what? This is list. This is another list. And simply based on this list, and this is what this is, we have a data frame and we have created. And now this data frame is storing data. And this data is printed out now. So data is now printed out. Fine. So we have here age and we have here city. And somehow we want to make it in numerical form. This one, this city, we are interested to make this one as a numerical data, categorical data, this city. How we can do? Somehow we have to discard that one. So simply we can do. So how we can do that? Our objective is to make dummy. That is called actually if we want to this kind of job. That is called we are going to create the dummies. So here we have a get dummies. It's a function, and get dummy function is working under PD, means pandas. That's why we have written here pd.get dummies. So get dummies would be work where? Which is the location? Location is data city, because in the data is the name of the file. So whenever we write data city, it means it's talking about the column, the name of the column, that is city here. So data city is the name of the column. Fine, means it is referring this one. If you want to refer this one, then we have to write data, single quotation, then city, this column. So we are interested to create dummy variables, dummies in this column. And now it is created, and those things are stored inside dummy features. So now if you want to see the dummy features, simply discarding this one. So here dummy features are created, and we are interested to see what is generated in dummy features. So looking at the dummy features, what are the things? See here, the dummy features, what we're having. In dummy features, we're having this one, this kind of thing. This kind of thing, 0, 1, 0, 0, 0 kind of thing. It means it's converted now, right, in numerical variables. Now, what's our objective? Our objective is to somehow those things to be incorporated with this one means somehow we have to concat this age with these dummies. Only then finally we'll get the database. So now what we need to do for that? So paste here. Now I have taken this age because this one is taken to a variable that is p. This data frame is taken to this column is taken to a variable that is p. And all the things, these things are available where? These things are available dummy features. So these things are available in dummy feature variable. So we are having this data frame and this data frame. Column Y. This is one column, this is 3 column. Now we want to merge, and we want to merge column Y's. So already we know for that one. So pd.concat, and here we need to have the first variable and this is second variable. Then comma, then x is equals to 1. X is equals to 1 means we are doing now column Y operation. When it becomes 0, then we are doing row Y operation. So column Y operation is done, and the part is stored in now a new variable that is a data modification 1, mode 1. So now data mode 1 is printed out here. So just to make the visibility more clear, just I'm writing here print this one only so that there will be a gap or space. So now if you run this one, then you can see here, see. So now we have this database. So this is now available, and now this part is added with this one, and that part is done by this line. This is the code for that one, concat. So here we have seen that how dummy variables can be created, and after creating the dummies, how we can merge together so that finally we can make the database. I think part is over here. So after that, what we have here. After that, in the presentation, what we had actually, after that we had like that. If we have a continuous values, right? I have done the code for if we have a continuous values and if we have to make it discrete. So here you see, if we have say numerical variables, if you want to make say categorical, then how we can do, because we have seen that in feature construction we have to do kind of things, right? So now we have a code here. We're going to see one by one all the things simply here. So we are doing that one here. So those things are created. So now this is the data frame. Now you can see here we have created. Not this one. Here just I have taken the code for different one actually. Not this one. I have taken the code for this one actually. This slide. This slide actually, right? If we have A, C, A, D, if you want to convert into say numerical variables, then how we can do actually? This one I have taken, right? So we have this one. So by this code we can generate this one. So here simply we have which one? Simply we have one list, another list, and here we have create the data frame, and finally data is printed out. Now our objective is to create like this, right? If we have this kind of B, C, A, D, now we want to make those things in the numerical discrete variables, 2, 3, 1 kind of thing. So how we can make, that's our question now, and that's our objective now here. So the option 1 initially, that I have many options here. So option 1 should be very easier so that you can understand easily from running 2, option 2 here. So here we have a 1 option here. How we can do? Simply we can do, right? So where we need to do, so here we need to do, right? What we need to do? Here, this kind of thing we need to do. So this column is referred as, because the name of the file is data. So now this column can be referred as data total grade. And what's our objective? Our objective is replace the values A, B, C, D by 0, 1, 2, 3 only, right? So we have represented the column, means where the operation has to be done. Dot replace. Our objective is to replace only. What do we need to replace? We need to replace A, B, C, D. With which one? 0, 1, 2, 3. So but we can do the same thing. We can do this conversion using the replace function, and the syntax of the replace function is like that. Means this kind of thing we're going to replace. This, the whole part within the third bracket, these things would be replaced by this thing. correspondingly. Then the first one would be replaced by the first one, second one would be replaced by the second one, third one would be replaced by third one, fourth one would be replaced by fourth one, right? So things are now replaced, and that is stored where? That is stored in now target. Say we have stored that one in target now. Okay, and now this target has to be added or merged with which one? Science merge this one and this one. So now this one we have segregated here. Simply we have written here the predictors data.ilog. All the this colon comma. This colon means what? This colon means there is no start, there is no end. It means what? It's talking about all the rows. And here we have the column part. We have the 0 and 2. It means it starts with 0 and ends with 1. So 0, 1. So it's talking about the column. So if we talk about this one, this thing is now stored in predictor. Which one is in predictor now? So if you want to see the predictors values one by one, if you want to see the predictor values, so here we need to write which one. Predictors, right? We have written predictors. Now you can run here, then you can see the values of the predictor, right? Already talked about, we have all the rows but two columns, this column and this column. These are the values of the predictors. Now what's our objective? Our objective is to combine this target with this predictor. So simply we can do it concat. So concat is written here. The concat is written. So predictor, comma, which one? Target. Target would be added later. That's why it is later. And this is x is equals to 1. That's a standard operation. So finally, it is stored in the data mode, and data mode is now printed out. So looking here, the finally, this is the final output. So this is the final output. Fine. So if you want to see here, the more than one, already I told you that we need to write here the print. So print data initially before doing the replacement, and this is we have after doing the replacement. So writing here. So after doing the replacement, so run now, we can see here both together. So this is the before replacement we have, and this is we have the after replacement. Fine. So if you want to have say a space here, you can make a new line or say print simply. This is one of the way, and the second way, just I'm showing you the second way simply here. Second way. Yeah, there are running whole part. Simply, but just by adding one line, we can complete this one. So up to here, the data frame is created. So up to here, the data frame is created. So if we discard this one, the same frame can be seen. Simply the same frame, right? Just we want to the whole part by a single line. So which one? Just we are changing. Which value we are going to change now? We are going to change the value of this column, total grade. We can change by this instruction, right? By this instruction, we can change. After changing this one, we're not going to keep it in a separate variable. Rather, we are going to keep it directly to this column. So it is also permitted here. So we have written the name of the column, that is data total grade. And simply the replacement kind of thing is executed here. Fine. So replacement is done here, and that replacement is reflected to the same column. And finally, the data is printed out because the name of the file is data, so that whichever changes were made, all the changes are stored in a column of the data file, the name of the file, that is data, in a column of the data. So now just we are printing the whole data here. So simply if we do, then we get output here. Simply right, we have changed in that way. And now if you want to use, in most of the cases this part is used because we are using machine learning, different kind of modules are there. So if you want to use a standard module, and then we can use simply this one. Here's the whole part. So by this part, we can create the table here. Table is created. Now we want to change this one. This changing can be done simply. We don't need to write many things, right? So we can have a very big database. If we're having very big database, then the things whichever we have seen earlier, those things cannot be done. For the big database, we need to do this one so that it does automatically all the things, right? So for the big database, if there are number of notations, number of A, B, C, this kind of thing, then it's very difficult to find out all those things, and you have to write all the substitutions or the replacement yourself on the code only when it happens. But So it is very tedious task if the database size is very huge. So in case of huge database, we're having here a level encoder. This level encoder is available in the pre-processing. That's why I have written here pre-processing submodule. And this submodule is available in this package, that is sklearn. In sklearn, we have a package, a submodule that is pre-processing. Under pre-processing, we have a function that is level encoder. So whenever we want to, already I told you earlier, whenever we want to execute one of the function within the submodule, then the submodule name has to be written here, the pre-processing dot level encoder. Means level encoder is now called, and it is storing where? It is storing LE, right? It is storing LE now. Now LE dot fit. Now LE is working. So LE is working where? That name has to be specified. So here that name is specified, that is data total grade. So here data total grade. Our objective is to apply this LE, means level encoder, to this column. So this column name is written here simply. Means where we need to fit this LE. LE means what? Is level encoder. So level encoder, we're going to apply or going to fit in this column. That's why we have written the name of the column here. Simply, this is the file name and this is the column name. In that way, actually, it can be represented. And then the e.fit. It's fitting here. And now the transformation has to be done, right? Transformation. Then the transformation. Here, the fitting is not done. If you want to see, you cannot see any output here, right? You cannot see any output here, right? Nothing is there. It is applied only. Now the transformation has to be done. Then lead dot transformation. This lead dot transform. Lead dot transform. This transformation is done where? In the same code, in the same column, you have to write the name of the column. Then automatically these transformations will be reflected on the right hand side. And on the right hand side, we have written the name of the columns directly. We did not use any other variable. So directly in the column of the database, this reflection or this transformation is reflected. And finally, all the things are available in a file whose name is data. Simply now we can print out a data here. So it is done automatically. You can see now it is done automatically. So this is the process whenever we have a big database, because whenever we talk about the machine learning, so it is talking about the big database. So if we have a big database, then we need to use this kind of thing for labeling. If you want to use, say, numerical labeling instead of this, say, this ABCD kind of thing, this is right. So we can do this thing like that. Now, so already we have talked that if we have this numerical values, and if you want to have, say, categorical values for those things, then how we can do? So here we have this, and we want to use the medium low kind of thing. So how we can do? Simply you can do. We have a functions available here. We have functions available. Simply we can do. So this is no, this should free. So here the transforming continuous values to categorical values. Simply we have a data here. See here simply here. So now initially the table is created. You know, using the data frame, using list and data frame, those things can be created. So this is the code for this one. So we have created the table. Now, no, data is not printed out here. So we have to print the data here. So data is taken out actually. So now this is available. So try to understand the data frame is created and that is storing data. So we have to show the data. We have to write the name of data here. Only then we can find out. So here simply it is created, this table. Simply this table is created here. Simply this table is created here, right? Simply the table is created here. The table is created here. Now we are interested to make like that, this kind of thing, right? So we have to give some kind of threshold. Yeah, we have given here just one line code is required here. So where we are interested to reflect the changes, we want to reflect the changes in price. So this price can be represented by file name and then price, data file, the price. Here data price equals to. Now we change all those things, right? So how we can do this one? For we have done this one using the NumPy. So NumPy is a good one, a good option here to do those things. So np.where we have it where data price greater than the data price greater than this 30 lakh, then we have written there high. Means if there is something that is greater than 30 lakh in the data price, then that one would be replaced by high. Then comma. Again, NP where we have written here data price less than 20 lakh, then that is level by low, and the remaining level by medium. So it is saying like that, if this one, else if this one, else this one. In that way, actually, it is working. So here I have one. If I have written the explanation here, if price greater than this, set high, else if price greater than set is, and else set medium. It says like that, right? So just cutting this one from here. So again, you see here that we have done this conversion using the NumPy. That's why I have written NP, and already we have imported NP, invoked here. Import NumPy as NP, aliasing NP, right? So NP can be called as NumPy can be called as NP here. So NP dot where, and this is the term what we need to do. If data price greater than 30 lakh, then it may be labeled as high, or it is labeled as high. Comma, if NP where data price less than this, then label as low, and then otherwise set as medium. So if we do, then all the reflections would be reflected where? In data price only. Here the reflection will be made here. So all the reflections are available here now, right now. And reflection is done, and finally all the things are available in the data set, and the name of the data set is data. So data is now printed out. So looking this one running, yes, now those things are converted. Fine. Simply we have converted all those things. So this part is done, and after that, what we have in our presentation, we had a kind of PCA. So we're coming to PCA now. So in PCA, that's PCA, right? PCA, we had a PCA. So now going to do PCA. Feature extraction, we're going to be using PCA now. So the whole code is here. Done. So done up to here. This is the code for the PCA, right? So the PCA, the package which is available for PCA, the package name is decomposition, and we have to import now PCA as a submodule. And here again we have imported one more submodule, that is standard scalar. Means we have done the normalization. So you try to understand, still normalization part is not discussed in our presentation. In our discussion we didn't discuss, but it's still just normalization is added here. Once I use the normalize, then again I delete normalize from here, then we see how the accuracy changes. So initially we're adding the normalization. So normalization talking about, say, changes the ranges of the data, or we want to keep the ranges of the data to a common scale. Using, say, standardization and normalization, we give the data to a common scale actually, right? So that's why standardization is done. Especially in some data sets, the standardization works, and for some other data set, it doesn't work. So in detail, we'll be talking about in our presentation. But that one is taken here, the submodule. This is a standard scale for that one is used. And this submodule is stored because it's a kind of pre-processing. Already talked about the things whichever we are discussing right now, all are belonging to data preparation or pre-processing. That's why these things are available in sklan.preprocessing submodule package. Within this package, this submodule is available. Now we are going to use this PCA, principal component analysis, in which database? In IRIS database, right? In IRIS database. In IRIS database, we're going to do now PCA. We're going to apply the PCA. So now it is divided as a predictors, and the target means the number of attributes, and this is the target. And again, you try to understand this PCA is applicable to only the inputs, not the output. We can find the inputs, and finally the whole input part can be represented by the components which can be extracted by PCA, right? So here that inputs are stored in say predictors, and somehow those inputs are, before doing PCA or before applying PCA, those inputs are normalized with this standard scale, right? And this standard scale dot fit transform Now I'm not going to, just I'm telling you here, these predictors. So we have our predictors here. So I can cut this one and I can show you one by one so that you can understand very easily. So if you write the predictors here, predictors here. So this is the input of iris datasets. These are the input of the iris dataset, right? So when we apply PCA, PCA is applied here, 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 right? So we have 1, 2, 3, 4. In the original database, we're having 4 attributes or 4 features. So if we want to reduce it and we want to extract new features like say 2, 3, or 1, then we need to do PCA. And with those constructed new features, we can predict the level of the iris dataset. Fine. So here we have the code. And here we have done which one? We have done standard scalar dot fit transform predictors. Means now all those predictors, what you're looking here, these predictors are normalized by which one? By standard scalar. And that is also stored in the same name, that is called predictor. So if you want to see now after normalization how the values are looking, then we can see that cutting this one. And now the normalization is already done here. The normalization can be done simply, right? Simply, that is called, actually here it is called standardization. When we do normalization, normalization takes a value within between 0 and 1. But you try to understand, especially in case of machine learning, in most of the cases, generally we do standardization, and that is called Z-score. And standardization can be done here in Python, because in presentation we have a theoretical formulation for that one. But in Python, simply it can be done a standard scale function dot fit and then transform, and then the data set or the data where we want to use this standardization. So here now we are interested to use the standardization in all the predictors, the inputs, right? So that's why predictors are written here. So now the standardization is done here, and that thing is reflected to the same variable. The name is a predictor, simply here. And we are printing now this predictor. Simply, I'm just running here, simple code. You see here, if we do the normalization after, sorry, standardization, after standardization, these are the values. These are the values of the 4 features of the iris dataset. Fine. So now we're coming here. So here we have applied now PCA here. And here you can give the how many feature vector you want, and how many feature you want to extract it from there. So in this code, just we have written, and that is represented by n components. And here we have written 2, means we are interested to create only 2 features. Out of 4, we are interested to create how many? 2 features. Now this function is stored to PCA, small PCA. Now this small PCA has to be applied. Where it is applied? It is applied like that. PCA.fit transform. So whenever PCA is applied, again .fit transform is used. Because actually the value is transformed to some other space. That's why the PCA comes under feature transformation. Under feature transformation, we have a feature extraction. That is actually feature transformation, right? So we are transferring the feature. It says that a feature, we are changing the feature from one space to another space now. So we are transforming the feature. Which feature we are transforming now? We are transforming now the predictors. And finally, all those predictors are stored where? These are stored in print comp. Fine. So in print comp, how many features would be? Only 2 features, because we have applied now the PCA for 2 components with 2 features, so that the features would be created or generated. The new features would be 2-dimensional, and those features are stored now in print comp here. So now if we print out this print comp, then we can see the values. This one is cutting from here. So now we are running to see the values here. So running the values. So see here, at last you can see, because we are having all the printf. So the data which are extracted now it becomes a 2-dimensional, and 2 dimensions becomes like that. So after applying PCA, the data is transformed into 2-dimensional data, and this is the description of the data. This is the description of the data. This is the whole database. Now the database is represented by only 2 dimensions. Fine, somehow we have to apply already transformation is done, right? So now we have to apply to the classifier whether after doing the transformation, the accuracy improves or not. We're going to see, because generally this PCA is applied for data reduction, for the compression purpose. It is claimed that without much loss of information. So we are going to see whether information is lost or not. If there is no drop of accuracy, then we can say there is no information loss, right? But if there is drop of accuracy, then we can say yes, there is information loss. So now doing this part. Now print com, because now have to this one, we have created these things, right? We have created these two columns now. So now these two columns we need to give the heading column name, because whenever we want to do or we want to use certain kind of operation on that, then column name should be there. But now if you say the column name is not there, you can see here this column name, no column name is there, no column name is there. Is there any column name? Looking, no column name is there, right? So now we want to give, this is the column 1, this is column 2. We want to give the name column 1 and column 2. So how we can give the column name? We try to understand. You can have a database without the column name, but later on you can give the column name by this code. This is a simple line. How we can do the column name of a data frame? Simply pd.data frame. Then data equals to, this is print comments here. You have to give the database. A database should be assigned to data here. So now this database is assigned to data. Fine. Now this comma column, you will write in column equals to what? We want to have two columns. Means this is the name of the first column, this is the head of the first column, and this is the head of the second column. So the first column would be PC1 and second column would be PC2. So after doing the columns, now this is the name of the dataset. We're having the same dataset. Dataset is not changed, just we have given here the column names. Now these column names, because we don't want to distort. I have done those things. Why? Because I have given those things, because I have written once this code and I want to use the code again and again. I didn't change anything. So somehow whenever some variables are created, those variables are given to the same name actually. So we have created this one, right? Now, so where we have a column name, one column name is PC1, another one is PC2, and it is stored here. Simply now this thing is stored in say predictors, because we're going to use predictors here. So now if you want to see the predictors here, so we can cut up to here. We're cutting this one, I'm cutting up to here. Then you can see that we have now the data, but data with the column name. So column name can be given here now. This, none. But here, see, we have a column 1 and column 2. Now column heads are here. It says column name. Simply, right? So already we have which one in the code? Already we have a two part. One part is the independent variables or the predictors, means the input variables, or you can say the features. Now features are represented by the predictors, and we need to have the output for the prediction. And already the output is stored in target. So now we don't need to segregate, because already target is in a target and predictor is in a predictor, but the content is changed now. Because in earlier cases, in predictor we have say 4 columns, but now in this case in predictors we are having only 2 columns because PCA is applied here. But simply the remaining code of the decision tree is same. I didn't change anything here. This is the code here to here. This is the code of the decision tree. I didn't change anything. And I'm not going to discuss now decision tree, because here the decision tree is not discussed in the presentation. So now simply, now if we apply the PCA, if we reduce the components or the dimension of the database, then we're going to see how the accuracy changes in the database. Fine. So now we are running simply here. See, at last you see how much is the accuracy. At last the accuracy is 88%. So you can see drops. So if already we have seen that without doing any PCA or feature reduction in case of iris dataset, if the same with same setup, if we use the decision tree, then the accuracy was 95%. But in this case, the accuracy dropped and it becomes 88%. So now we can conclude from the perspective of this database, only from the perspective of this database, we can conclude that whenever we reduce the database or database size, then automatically some part of the information is lost. That's why the performance degrades, especially in case of iris database. But if you try to understand, if you want to claim something as a research paper, then you have to do this kind of experimentation in number of database. And then finally, you can conclude based on your experimental results. Fine. So now here we had a 2 and we got this kind of result. Now if we change the number of this one features, say now we're changing it to 3 features. We made 3 features. Clear? So component become how many? 3. It's already in the iris database we are having 4. Now we are going to create how many features using PCA? 3. That's why 3 is given here, right? So 3 features will be created here, but keep in mind we have to give 3 head names because there are PC1, PC2. Similarly, we can have a PC3 here. So making that one simply we can have PC3 here, and name is here. This is PC3. So simply 3. We have created 3 database now, so you can see those things here. If you discard here up to here, discarding the decision tree and just looking only the transform database, and where we are interested to create only 3 components out of 4. So looking this one now. So here you can see at the finally we have a now the transform database. In this transform database we have a PC1, PC2, and PC3. Fine. PC1, PC2, PC3, we have now 3 dimensions of the database. And now we are applying this transform database to the decision tree with the same setup and looking how much is the accuracy changes. There is no change of the accuracy, 88%, no change. If we change the number of components, if we make it as a 3, then still there is no change of the accuracy. Now see, I'm just making one more here, making it 1 only, simply 1 only, right? Only 1 dimension is created. That is the principal component only, right? So we must have only 1 head here. So making 1 head here, 1 head here, up to here. So now, so you have to see, and it will be very clear for you that things are happening like that. So we are interested to create only 1 dimensional database now. So we have a 1 dimension now. Fine. With the 1 dimension, we want to see the accuracy of the database and how much it becomes now. So accuracy becomes how much? See here now it becomes how much? The accuracy becomes 88, right? So the conclusion is that in case of iris database, if you use only 1 component, but still there is no change of the accuracy, right? Means there is a drop. If we use this 2, accuracy doesn't improve. Again, it is 88%. If it is 3, then again it is 88%. It means what? The principal component, the 1 principal component that is extracted from the PCA, that principal component is having the actual information. Other component doesn't have any information if we keep the principal component with them. Okay, so that's about the PCA principal component analysis. Do you have any questions, participants? You are not putting any questions. After that,
Any questions, participants? Write in the chat box also.
so now one thing I'm going to show you here. So the thing here we have done already talked that we have done the standardization, means we have done scanning kind of thing is done here. Standardization is done here. If we want to do the same thing without doing the standardization, here I have the code. Then I'll conclude something here. So you see here in this code, we didn't do the standardization here. We didn't do because this standardization is not done here. See here simply a standardization is not done here. The part what we have done earlier here, you can see this part standardization is a transformation of the features to a common scale. It is done here. There is standard scalar. That standard scalar part is not done here. I didn't do here, right? And again, I have constructed how many features here? 2 only. So without doing standardization, if we do the experimentation and if we apply the PCA, then what's the accuracy looking on that? We didn't do the standardization. That's why the values are like that. Values are like that, values are like that, and simply the accuracy is 91%, right? So if you don't do the standardization, here the accuracy improves. So keep in mind that, especially when we discuss about normalization and standardization, it says that whenever we do normalization and standardization, the accuracy improves. But you try to understand this normalization and standardization is not applicable for all the database. when it is applicable and when it is not, during the discussion we'll be talking on that. So just I have shown you one experimentation that if you do the normalization or the standardization, still for some data set, the performance cannot be improved. I think it is done here. After that, already talked about the feature selection, right? Feature selection part we have discussed. So now today I'm going to do some kind of feature selection here, how to do. So in feature selection, we discuss about which one? We discuss about correlation coefficients. Correlation coefficient, we talked about that, right? So in correlation coefficient, what do we discuss? Coming there, it's already discussion part is over there, so I should not discuss again. Just I'm doing the experimentation, then I'm trying to tell you what is the conclusion on that. So here, just we have taken the same data set, this iris data set, and we are trying to find out the correlation coefficients, means how the features are correlated with each other. If the features are very much correlated, then what you can say? They are the redundant pair. So one of them can be omitted from the pair. So that correlation thing can be done simply by core. Core is for the correlation. And what we have done, how we have written this program, yes, we have invoked and imported the database, and database is in F1. Now what we have done in core, we have stored f1.core, and this core is a function. By this core, actually you can find all the correlations among the features which are available. Now all the correlations are stored here in core. Now using this one, we want to create one heat map. We can create or we cannot create the heat map. But using heat map, generally in most of the papers and research articles, you can see that using the heat map, things are being shown. So if you don't know the heat map, it seems that it's a big thing. No, it's a simple thing only. In heat map, actually, it shows different correlation of the different pair of the attributes or different pair of the features. So in our iris data set, we are having only 4. So we can have a different kind of pairs and looking at how they are correlated. And for that, this is the code actually. Very simple code. And the CBON is used here as SNS.heatmap. Simply in heatmap, in CBON, we're having a function that is called heatmap. Simply if you write the core and if you write those things, then automatically it shows the heat map. Looking on the heat map now. Because it's a map, because some kind of say figure is going to be made here, that's why we have invoked here. This is matplotlib.pyplot, PLT as PLT. See here, that's the heat map actually. This is the heat map. Simply, this is the heat map. In the heat map, what is the outcome? And see here in the in this axis, what do we have? Sepal length, sepal width, petal length, petal width. And here we have a petal width, petal length, sepal width, sepal length. So here, this is the score or the correlation. And you try to understand, if you don't write anything here, then it finds the correlation based on Pearson correlation coefficient. And Pearson correlation coefficient is already discussed in the presentation. And it finds the correlation between two features, how they are correlated. So if you don't write, it means what? It is a Pearson correlation coefficient. So using this Pearson correlation, the coefficient or the correlation between petal width and sepal length, that is 0.82, means they are highly correlated. Now if you find the correlation between sepal length and petal length, that is 0.87, highly correlated. Similarly, sepal width and here the value is minus 0.11, so they are not related at all. And now the same thing here, we have a sepal length and the sepal length. The value is how much? This is 1. So for all the cases, for the same feature, the value would be 1 because they are exactly similar. That's why in the diagonal, you will get all values 1, 1, 1. So here, similarly, if it is a sepal width, and if you find the correlation with this one, petal width, sepal width and petal width, the value is minus 0.36. It means what? This petal width and this sepal width, they don't have much correlation with each other. They are completely opposite to each other. Similarly here, sepal width and petal width, same thing. All the coefficients which are extracted here is talking about how they are related. And that one can be seen very easily by a map that is called heat map in correlation coefficient kind of thing. In correlation, in finding correlation of different features, we can use heat map simply. Fine. So this is over now, and then again we have another one that is in feature selection. We have here feature selection. Today I'm not doing any feature selection kind of thing because it's still the feature selection part is not over. Feature selection part is not over. That's why. So before that, before that, one thing, right? One thing we have discussed, that information gain, even if the part is not totally discussed, the information gains less mutual information. I can show you the slide here. Here we have done some kind of discussion here, but we did not discuss due to paucity of time here in this case. Just we have written here, measure of feature relevance, by which one mutual information and information gain. Using mutual information and the information gain, we can find the feature relevance, whether the feature are relevant for this particular problem or not. So in this case, if you find the feature relevance of habit, then it says that whether habit is significant in solving the classification problem or not. If it is 0.5, then we can say the significance of this habit to find or to solve this problem is 0.5. Similarly, if the if is 0.6, then we can say the significance of this if is to solve this problem 0.6. If this one is 0.7, then we can say the significance of footwear to solve this problem is 0.7. So out of 3, the most significant activity is the footwear. So we have a lot of calculations there, mathematical calculation. So by which we can, what we can do, we can find the feature relevance, whether the feature is relevant to solve the problem or not. That feature relevance can be done simply in Python. That is, again, see here, there's a mutual information. How we can, this is the mutual information. We're going to find the mutual informations of the features to solve the problem. So here again, same thing, we have the Irish problem. So in Iris, we know that how many input variables we are having. We input features, we are having 4 input features. So if we run this code, then we can find out each of the features is having how much impact in classification of Irish problem. So here we're going to use now the information, mutual information. So see here now, running the code and looking how much relevant which attribute. So now running this one simply here. Just here pandas is called and this numpy is here, and you see here just we have taken one more here, and that is called mutual info class if, and it's a submodule, and this submodule is available in this package. The name of the package is scalan.feature selection, because it's a part of feature selection, because we discussed this one in under feature selection. So it's a part of feature selection. That's why this submodule is available within this package. Now the whole data set, Irish data set, is invoked and is stored here. And similarly, it is broken into 2 parts. This predictors is talking about the number of features, and there are 4 features. And this is talking about the class level of the Irish problem. Fine. Now fit equals to mutual info class if. It's a now function. Within the function, just we have given 2 arguments, and the first argument is the predictors, means the number of input variables, or that is called the features, number of features, and then we have given here the target, means that's the output. And then now if we run, then automatically what we can do, automatically we can find out the impact of different features will be calculated, and those will be stored here. Fine, in fit. And finally fit is printed out. And here print, this one means what? Just we try to print out the column name so that you can understand for which column the significance is what. That's why we have given. So initially we're cutting it out so that you won't have any confusion, cutting it out, right? So now all the relevance or the mutual information is stored, it is stored in fit, and finally fit is printed out here. So looking now this one, see here that for the first column or for the first feature, this much is the relevance level. So this is the relevance level is 0.4. For the second features, the relevance level is 0.2. For the third one, the relevance level is 0.9. Means third feature is very much important in classifying in the classification of the problem, because here the impact, or you can say that the significance level is 9.9. So whenever the significance level is high, it means what? The feature is more significant. Similarly, if you see here the third one, fourth one, then again this one is more significant, right? So these are the scores. So based on these scores, we can say whether the features are significant or not, whether the features are relevant or not. So if you find the relevant, then these are the most relevant feature. And this one is a bit relevant feature. And this is what? This is a less relevant feature. None of them is a irrelevant feature. If it is a irrelevant feature, then the irrelevant score may be negative or can be 0. But we are looking, none of them is 0, right? So what we have here, we have print column name of the data set. So printf predicts the column. It's a now data set, you can see it's a data set of the features. And then the columns are available there. There's the columns only here. So now printing out, so we can find name of the column. The first name is what? Sepal name. And second name is what? Sepal width, pedal width, the pedal length. So okay, try to understand in the iris problem to classify the iris problem, which is available in machine learning repository. The first feature whose name is sepal length, its relevance is 0.4. So it's less relevant, right? And the sepal width, this is less relevant because here it is 0.26 only. And this is pedal width and pedal length and pedal width. Both are having high significance in predicting or in solving the classification problem of iris problem. So in that way, you can find the feature relevance or the feature significance in Python. Thank you, everybody. Today's session is up, I think, and the next session I'm just telling you what we're going to see. I know that it's not possible to cover up, but every day I want to cover which thing we can cover next day, those things, because most of the things actually what you are familiar with, feature selection, some of the classifier, those things actually didn't come yet because generally what we do, we solve some kind of algorithm. So this is KNN algorithm, this is decision tree algorithm, this is neural network. But you try to understand before using those algorithms, we need to process the data. So if you know all the processing of the data, if you know all the classifier, regressors, and all the association mining algorithms, clustering algorithms, then you can say a bit machine learning, you know how to do which algorithms are available and what can be the issues and how those issues can be sorted out. Then only you can say that. If you know only one algorithm, many claims that I am doing some working in machine learning, just he knows neural network something, right? It doesn't mean so. Means you're using one of the tool of the machine learning. Whenever you say I'm working in machine learning and I know machine learning, means what? You know all the issues of the machine learning, right? Or model about all means what can be the issues, what are the algorithms available, not to solve the problem, not for the classification only, for other issues, what kind of techniques are there, you have to know. Only then you can say that you know machine learning kind of thing. So after that, what we have in our hand actually to discuss, we have many things to discuss actually here. So we have one lecture left. I'll try to cover up this thing. Feature selection still is not discussed, right? In feature selection, you may be familiar with sequential forward selection, sequential backward selection, right? And a floating sort selection. Those things are available. After selection, then we'll be talking about the data normalization. If it is not, I'll skip it. The data normalization. Then we'll come for the training, right? In the training, I'll come for the training. In the training, generally whichever you do, 30% for 70% for training, 30% for testing, that is called holdout method. But you try to understand holdout method doesn't work for all the cases. And holdout method is not accepted in some research article in the machine learning community. For that, we need to do cross-validation. So what is the foundation of the cross-validation, right? If we get time, that those things will be discussed in our presentation next day. Thank you, everybody. Many things I have, but I cannot discuss all those things. I have included some of the classifier here, but it's not possible to cover up. Thank you, everybody.
Thank you so much, sir. Any questions, participants? So participants are asking regarding the textbook names. Can you show it, sir, or tomorrow you will show?
I'm telling you one thing. I will write number of textbook, but you will not get any context from exactly any of the textbook. You try to understand. It's not like that. I have copied from textbook and I have say march all those things here. this is my experience, because I'm teaching this one, I'm doing research on that actually. So this is my sequence. You'll not get any book in that sequence as per my knowledge. There can be some books, okay, but as per my knowledge,
just as they are beginners there, so they are curious.
yeah.
So from where they have to start.
But the books, which books I refer, I have taken some of the references, some of the problems, right? I write all the book names, all the reference URL at the end of the PPT, because I'm going to give you the PPT right next day, but I have to write all those things, right? References, kind of thing, all kinds of things I have to write. But my request is that you don't publish the PPT. Right? You try to understand that we are faculty and doing some job in some prestigious organization. So you don't publish, and that's why actually before giving this PPT, I have to add all the references at last actually. Okay, and
thank you so much, sir.
Thank you, everybody. Thank you.
Thank you so much, sir. Thank you, participants. So I'm sharing the feedback link. Please, all of you, give your valuable feedback. Thank you so much, sir.